So let's start with a very simple problem. We want to solve a simple one-dimensional Poisson equation using a numerical method. Okay, so basically we have a one-dimensional computational domain going from x equal to 0 to x equal to L. Okay, x equal to 0 on the left end, x equal to L on the right end. On the left end, I have a prescribed phi boundary condition. On the right end, I also have a prescribed phi boundary condition. This is my governing equation. Okay, and for now, let's say S of phi is just a function of x or a constant. Okay, so those are my boundary conditions. I already mentioned that phi at x equal to 0 is phi L, phi at x equal to L is phi right. The closed form analytical solution, you can easily integrate that, okay, provided S of phi is a constant. So this is with the assumption that S of phi is a constant. Okay, so this guy, you should write it down here. All right, so that's your analytical solution, and we're just writing that because we'll use that later for verification of our solution. So now we want to solve that same problem numerically. Okay, so what we will do here is, now if you go back here, this is a continuous function that we have derived analytically. We can pretty much find the value of x anywhere from that solution. Okay, but in the numerical solution, what we are going to say is, we are not going to try to find the solution everywhere. We are going to try to find it at prescribed locations called nodes. Okay, this is kind of like an experiment where you fix or you stick probes in certain locations and measure whatever you want to measure at those prescribed locations rather than anywhere within that body. Okay, the node spacing in general could be equal or unequal. Here I have shown a picture where at least I'm trying to show that they are equally spaced, and the spacing, let's say, is called delta x. Okay, so if they are equally spaced, delta x is the total number of the total length of the domain divided by n minus 1. Why n minus 1? Because if I have n nodes, I have n minus 1 spacings. Okay, so my delta x is L over n minus 1. So what we want to do is, of course, we want to have a digital computer solve this problem, so we must convert the second derivative in our governing equation to an algebraic form. We talked about this already. That's our goal. Okay, and our objective is really to express the derivative in terms of the nodal values of phi, so that we can treat those as unknowns and solve for them. Okay, that's what we are trying to do. Any questions? All right. So to do that, to convert the second derivative to a bunch of algebraic equations, what we are going to do is we are going to employ Taylor series expansions. Okay, so here I have drawn just 3 of those points that I showed in the previous slide. Okay, just pick any 3 of those points inside the domain, and I have labeled them as I plus 1, I minus 1. They are equally spaced, at least for the derivation we are doing right now. Okay, delta x and delta x on both sides. And another alternative notation that people often use are, the central node is called node naught, the one on the right is called node east, and the one on the left is called node west. Okay, if you have 2D, you will have north and south. All right, and if you have 3D, sometimes they call it forward and backward, or upstream and downstream. Okay, so this particular picture that I've drawn here, this is typically called a stencil. Okay, so very often I might tell you, go show me your stencil diagram. So this is what I expect you to show me, that okay, this is what my stencil looks like. So we are going to perform 2 Taylor series expansions, one forward and one backward. Okay, and this is what it's going to look like. So you all know Taylor series expansions. Okay, so what we are doing is, phi is a function. This is like your f. that we use in math all the time. Okay, here we are calling it phi. So we are saying phi at the eastern node can be expanded about phi at node naught using a Taylor series expansion where I have phi naught plus delta x times d phi dx plus delta x square over 2 factorial d square phi dx square, and so on. Okay, and similarly we have a Taylor series expansion in the negative x direction, which gives us, as you can see, some of these terms come out to be negative. Okay. Now, very often, so this is the first time I'm introducing this. So what I'm going to do now is I'm going to actually explain to you why you get the positives and why you get the negatives and when you get the positives, when you get the negatives. Okay. This is the only time I'm going to show you this because I want it to be absolutely clear in your head. Okay, I don't want you to do any kind of guesswork that, oh, maybe I should change the positive to a negative and try if I get the right expression. No, this is math. You have to know what you're doing. Okay, so I will just go through this briefly and show you one time. Oops. I think I messed up. Okay, so here is what's happening. Okay, so here is my x coordinate in that direction. Okay, and this is my x naught, this is my x east, this is my x west. Okay, both of them are at a distance delta x. Remember, delta x is the distance. It's always a positive number. Okay? So, Taylor series expansion tells us, so suppose I want to expand this point about that point. Okay? So what I'm going to say is f at xw is equal to f at x naught plus xw minus x naught times f dash at x naught, okay, plus xw minus x naught square over 2 factorial divided by times f double dash at x naught, okay. And then you can have other terms here. And so on, right? Anyone here who doesn't understand this? This is pretty clear, right? So this is just Taylor series expansion as you see for the first time in your math book. Okay, now think about this. X naught xw minus x naught, what is that equal to? Is it plus delta x or minus delta x? Minus delta x. Okay, so this guy here is equal to minus delta x. All right, xw minus x naught squared, this is minus delta x squared, which gives me back a plus delta x squared. Okay, xw minus x naught cubed, this is a minus delta x cubed, which gives me back negative delta x cubed. Okay, if I were to do the same Taylor series expansion in the positive x direction for xe, all of these guys would come out positive, because in that case xe minus xo would be just delta x, not minus delta x. Okay, so does everybody understand why we get the minus sign in the negative direction Taylor series expansion only for the odd terms? Okay, in the even terms, because we are doing square and to the power 4 and to the power 6, they become positive. Okay. All right, so that's our two Taylor series expansions. When we add the two expressions, this is what we get. On the left hand side, we get phi east plus phi west, and then we have a 2 phi naught, and then you see the first derivative cancels out. Okay. The second derivative, on the other hand, gets added up. So we have a 1 over 2 factorial, which is half. Half plus a half gives us 1. So we get 1 times delta x squared times d square phi dx squared. All right. So that's this guy here. And then the third derivative again cancels out. This and this canceled out. This and this canceled out. Fourth derivative again gets added up. 1 over 4 factorial is 1 over 24. Okay. So 1 over 24 plus 1 over 24, that gives you 1 over 12. Okay, so you have delta x to the fourth divided by 12 times d4 phi dx to the fourth, and so on. So the next term will be the sixth order term. The fifth order would cancel out, and so on. Okay, everybody get that? All right, so what we're going to do now is we're going to rearrange that and write our second derivative, which is what we are trying to derive, the expression for the second derivative at node naught, because our governing equation has d square phi dx square equal to s phi. Okay, so that's our second derivative in terms of everything else in that equation. Okay, what's that everything else? That everything else has two components. It has these nodal values of phi, which we are trying to solve for. Okay, this guy. So we have these nodal values. Those we don't know, but we are trying to solve for them. Okay, and then we have this additional term which involves the fourth derivative. Okay, now of course, if we don't know phi, how can we even know the fourth derivative? We don't, obviously. Okay, we are trying to find phi, obviously. So fourth derivative is not known. So really our only option here is to say, forget that fourth derivative and whatever terms we have beyond that, throw them away. Okay, with the understanding, of course, that it will give us an error. Okay, because the exact expression for d square phi dx square includes all those higher order terms, but now we are going to throw them away, so therefore we have incurred an error. Okay, so what we have really is an approximation of the second derivative using finite difference, which has only the nodal values of phi that we want to solve for, okay, with an accompanying error that looks as follows. Okay, everybody get that? So one takeaway message from this is that every time you convert a differential equation to an algebraic equation, you will have an inbuilt error in it. No matter what you do. I mean, you could go 50th order, you will still have some error. Okay, you could go make this really complicated, and we'll talk about the order of the error and all that, but you could make it really fancy, but you will still have some error. So if you go back to lecture 1, and I talked about the fact that when you do verification and you compare the numerical answer with an exact analytical answer, there will still be always an error. Okay, that's the error I'm talking about. So they won't perfectly match. There will always be some error. Now, in some cases, the error may vanish. Why? Because let's say your phi is a quadratic function. Okay, of course the fourth derivative of that function is 0. Okay, so even though there is that error term, for that particular case, it so happens that it's 0. Okay, but that's on a case-by-case basis. In general, there will be an error. Okay. All right, let's talk a little bit about this error. So first of all, this is known as the finite difference approximation to the derivative, which is what we're trying to do. Okay, and then this is the error introduced by the finite difference approximation in converting derivative to an algebraic equivalent. Okay, since the error is introduced by truncation of the Taylor series, remember we have this guy plus the higher order terms. Okay, we truncated it basically. Okay, so that's why it's often known as the truncation error. It's sometimes also known as the discretization error because it's something we got when we tried to discretize the PDE. Okay, any questions? So what are some of the properties of the truncation error? Okay. One of the things to note is that it is proportional to delta x squared. See right here, epsilon is proportional to delta x squared. Okay. What does that mean? That means if I double the number of nodes, my error will go down by a factor of 4, not by a factor of 2. Okay. If I make my mesh 10 times finer, my error will go down 100 times. Okay. What it also means is that if I make delta x really, really small, my error will vanish completely. At some point, what will happen is that the error will become smaller than the round-off error of a digital computer. So if you're storing your numbers in single precision, that's 8 digits. Beyond 8 digits, you will not even see that error because, you know, the computer will basically eat it up. Okay? So this is an important issue, the fact that the error approaches 0 as the mesh is refined. And that is why we always endeavor to use a fine mesh for accurate calculations. Okay. Now, there is nothing which says that, you know, the error has to be, okay, let me just talk about this. So we're pretty much talking about the leading order error term. There are other terms, as we said. The next term will be the d6 phi dx to the 6, and it will have a delta x to the power 4 in front of it. Okay, if you follow through with the derivation. Now, why do we not care about those higher order terms? Well, think about it, if delta x is reduced by a factor of 2, delta x squared goes down by a factor of 4, delta x to the 4 goes down by a factor of 16. So those higher order terms are decaying even more rapidly than the leading order term as you define the mesh. So you don't care about them. What you really care about is the leading order term because that's what's dominating your error. Okay, all those other terms are minuscule compared to the leading order term. Okay, so that's why we don't care about the leading order term, the higher order terms. We only typically, when we write down error expressions and analyze it, we typically only analyze the lead order term. Okay. Okay, the fact that epsilon is proportional to delta x squared, this guy here is known as the order of the scheme or the order of the finite difference approximation. Okay, there is nothing which says that it will be always x squared. You could develop a scheme which will have order just 1. So epsilon is proportional to delta x, which is still fine. It still satisfies the criterion that as I refine my mesh, my error will go down. Okay. Now, if you have a situation where you have delta x to the power some negative number, then that's a trashy scheme that you have developed, because that would mean as you refine the mesh, your error goes up. Okay. Don't even bother to use it. It's useless. So this is known as the order of the scheme. Okay. Now, here we did the derivation for equally spaced nodes, and that's why the order has come out to be a nice number like 2. Sometimes what happens is if you use unequally spaced nodes and try to do the derivation, you will find that it's not very clear whether it's first order or second order. It will be somewhere in between. Okay? So that's something to keep in mind, that the order of the scheme is not always well defined. If it's equally spaced mesh, then it's easier to derive and pinpoint. If it's not equally spaced, then, you know, at best you can say it's going to be somewhere between first and second order. Okay? All right, so in this case it's second order, and as I said, as long as it's a positive definite number, it's a valid scheme. Now, recall that we did 2 Taylor series expansions, one forward and one backward. Okay, so one we did east about naught and the other we did west about naught. Okay, So one in forward direction, one in the backward direction, and that's why this kind of a scheme is often called a central difference scheme, because we used one node in the forward direction, one in the backward direction. We could have derived a second order or an expression for d square phi dx square using two Taylor series expansions both in the forward direction or both in the backward direction. Perfectly valid. Okay, nothing there which says we cannot do that. Okay, that would be perfectly valid, but that would not be a central difference scheme. Okay, that would be a forward difference scheme or a backward difference scheme. Okay. So let me talk a little bit about the general procedure for deriving finite difference approximation. So I give you one example. Okay, now in that example, as you saw, some terms nicely canceled out. Okay, and that may not always happen. So let's take a very general example and see, okay, if I'm asked to derive a finite difference approximation for some derivative, how do I do that? So first of all, let's set some ground rules. Rule number one is that to derive an nth derivative, you have to use at least n Taylor series expansions, okay, or n plus 1 points in your stencil. Okay. Consider your second derivative. If you want it, so here in the example that we derived the second derivative. You cannot derive a second derivative using just 2 points. It's impossible mathematically. Okay, 2 points you can only represent by a line. You can't say that, okay, the line bent this way or that way. It's impossible. You need at least 3 points. Okay, so that's the whole idea, that you can't do one Taylor series expansion and 2 points to derive a second derivative. You must have 2 points and 2 Taylor series expansions. Now you can go beyond that. You can use 5 points and 4 Taylor series expansions to derive a second derivative. What will end up happening is, in that case, you will get a higher order scheme. Instead of your error being second order, you will find that your error will be maybe fourth order. Okay, so the order of the scheme can be increased by using more Taylor series expansions. Okay, and later on in class we will talk about how to do higher order differencing. Okay, towards the end of this class, maybe 2/3 of the way. For right now, we will just stick to the second order scheme that we are talking about. Okay, but that's one of the rules that you have to follow. So here is an example. Let's say we want to derive a finite difference approximation for the third derivative now. Okay, not the second derivative. So our rule says that we need at least 3 Taylor series expansions and 4 points according to the rule. Okay, now whether that will in the end give us first order scheme or second order scheme, we don't know. All we can say is it will give us a valid scheme. Okay, it remains to be seen what the order of the error might be in that case. So I have arbitrarily chosen 3 points or 4 points as node north, node east, and then I have taken 2 points in the negative x direction. I could have taken west, north, east, and then east, east. Okay, I've just chosen to do what I've shown here. So here are our Taylor series expansions. The first one is the one in the positive x direction, so going from east to north. Okay, now one of the other things I want to point out here is sometimes I see students getting confused as to, should I expand phi naught about phi east or phi east about phi naught? Which way should I go? This is a very common confusion. Okay, the answer to that is your pivot point. Remember, here, let me go back to what I derived here. Okay, so when we do Taylor series expansions, this point, the point about which you are doing the expansion, okay, that is called the pivot point. This guy here. Okay, so the rule is, if I want to derive f double dash at naught, or what we are calling d square phi dx square at node naught, then my pivot point has to be node naught. I shouldn't be doing x naught is equal to x, or f of x naught is equal to f of x west and something, because that's then going to give me these derivatives at x west, not at x naught. Okay, but I'm interested in the derivative at node naught, so therefore I should use the pivot point as node naught. Okay, so how you do the Taylor series expansion, whether it's not about west or west about naught, is determined by what are you trying to derive. If you're trying to derive the derivative at node naught, then your pivot point better be node naught. If you're trying to derive the derivative at node west, then your pivot point should be node west. Okay? Simple enough rule. So just remember that. Okay, so we have done the two Taylor series expansions, one in the positive direction, one in the negative direction, which we already had, and then I've added another one which is 2 delta x spacing away in the negative x direction. And again, you see that the even terms are positive, the odd terms are negative. Okay, and then instead of delta x, we are using 2 delta x cubed, and so forth. All right. So now the question is, I have 3 equations. How do I manipulate these to get d cubed phi dx cubed? It's not obvious. If I had 2 equations, it's pretty obvious. Then you could say, well, I just subtract one from the other. That should keep something here, cancel out some of these terms, and so on. But now I have 3 equations. So the question is, how do I manipulate them to get d cubed phi dx cubed? Okay. So the general procedure is as follows. What you do is you arbitrarily multiply the 3 equations by 3 constants a, b, and c. Okay, so you say a times equation 1, b times equation 2, c times equation 3. Okay, and now you set up equations, algebraic equations for a, b, and c. How do I do that? Well, there are some things that we need to set as our targets. For example, if I'm trying to derive d cubed phi dx cubed, I don't want the first derivative sticking around anywhere. It doesn't serve my purpose. I want to cancel it. Okay, so what am I going to do? I'm going to make sure that the coefficients of the first derivative add up to 0. Okay, so that would give me a minus b minus 2c equal to 0. Let me just go back to that equation. So you see a times delta x, b times minus delta x, c times minus 2 delta x equal to 0. That basically gives me this equation. Okay, because delta x cancels out. Similarly, I want to cancel the second derivative. So second derivative, if I look at this, I would have a times delta x square over 2 factorial plus b times delta x square over 2 factorial plus c times 2 delta x square over 2 factorial equal to 0. Okay, delta x square over 2 factorial is going to cancel out, and it's going to give me this equation, a plus b plus 4c equal to 0. Okay, for the third derivative, I don't cancel it out. I want to set its coefficient equal to 1. Why? Because I want 1 times the third derivative equal to something. That would basically give me the third derivative. Okay, so I do the same thing and I set up the third derivative. Again, if you go back to your equation and look at the terms and add them up, this is what you're going to get. Now the delta x cubed doesn't cancel out because on the right hand side I have 1. Okay, so I basically have a times delta x cubed over 3 factorial plus b times minus delta x cubed over 3 factorial plus c times 8 delta x cubed over 3 factorial equal to 1. And when I simplify that, I end up getting that equation. Okay, everybody follow that? So now I have 3 equations with 3 unknowns a, b, c. I can solve it. Pretty easy to solve. Just a little bit of algebra, and those are the answers I get. A equal to 1 over delta x cubed, b equal to 3 over delta x cubed, and c equal to negative 1 over delta x cubed. Okay. My d square phi dx cubed is a phi e plus b phi west plus c phi west west minus a plus b plus c phi naught. Okay, that comes from the 3 equations that we had earlier. So now I have my A, B, and C. I plug them in, do a little bit of algebra. This is what I end up getting for my third derivative. I say approximately because, of course, there's an error. Okay, I've thrown away the higher order terms. If I take the higher order terms and compile the error, which is going to be A plus B plus 16C times the fourth derivative term, the error comes out to be negative 1/2 times delta x times the fourth derivative. Okay, notice that in this case the error is only first order. When we derived the second order, we got lucky. Why? Because there were these odd terms that canceled out and we got second order accurate. Okay. When we do third order, because it's an asymmetric distribution of points that we are choosing, we don't get so lucky. Some of the terms don't cancel out and we end up getting only a first order accurate error expression. Okay. So I would highly encourage you to sort of go over this example and work it out yourself a little bit, rather than just counting on the fact that, okay, these are the answers for A, B, C, and this is how you get it. Okay, so just do it yourself once to be comfortable. Any questions? All right, so we'll stop here, and next class we'll come back and continue with this.